So in this video, I'm actually going to open up our optimizer here. Here it is. And I'm going to go through all of the options and explain what everything does. Now, if you recall from our diagram, the optimizer component represents the particle swarm optimizer. This is completely separate from the model, which the optimizer essentially treats as a black box. The optimizer ships a set of input values over to the model. The model takes those inputs and spits out a predicted output. That output is then plugged into our fitness calculation, and that fitness value for the particle is sent back to the particle swarm optimizer, which updates the particle with the new fitness. This basically continues until we hit one of our stopping criteria. So let's look at our optimizer setup. Our model selection box here is obviously what model we're looking at for the optimizer. It could be a neural network model, or it could be some other type of model that you've defined. It could be a curve fit model or a custom model that you code yourself. Our population size is the number of particles in the swarm. See my last video of the particle swarm visualizer to see what a particle swarm looks like. The maximum evaluations is the number of model interrogations that the optimizer will allow, in this case 150,000. That does not mean per particle, it means total. So the number of actual particle updates for each particle is going to be the max evaluations divided by the population size. It also means that if your model takes a full second for each evaluation, this optimizer could potentially take 150,000 seconds. That would be exceedingly rare, but you can easily get into long running times if you have this value set very high with a large model. This next option, optimize only if any initial value has changed more than min% from its value the last time the optimizer was called. So that's basically a feature used to minimize the amount of churn on your inputs due to calling the optimizer over and over when we're at a stable operating condition. And basically what this is going to do is look at the initial / fixed value column and evaluate whether it's changed more than this minimum % since the last time the optimizer was called. When I click this button, this column appeared. If I uncheck it, that column's going to disappear. This option is a little bit outdated now that we've added some new features into the optimizer. The distance penalty for one, and also the fact that every time the optimizer starts, it utilizes the current initial conditions as one of the particle positions. So one of the particles is seeded with the current operating conditions. So if the current operating conditions are optimal, especially when you use that feature in combination with the distance penalty, it pretty much ensures that the inputs aren't going to move around unnecessarily. This distance penalty active flag here is basically something you can change programmatically. If you don't want the distance penalty to apply, you set it to 0. If you want the distance penalty to be in effect, you set it to 1. You can just as easily hard code it. So our input constraints here represent every input of the model. Now, pretty much anytime you're using the optimizer, you're going to be setting the minimums and maximums for each input in the optimization programmatically in the logic. Depending on operating conditions, you may want certain inputs at certain value ranges, and that's pretty much always the way we have it set up. We rarely hard code these values. Fixed or not fixed is whether that particular input is free to move or not. If this value evaluates to 0, then it's not fixed. So that input will be free to move in the optimization. If it's set to 1, that input will be stuck where it's at. And where it's at is defined by the initial / fixed value column. Now remember that one particle in the optimization is always going to be seeded with these values. So what you can do is bring in the current operating condition, or you can also plug in the most recent output from the optimizer. And the distance penalty here is a penalty that's applied based on the distance the particle is from the initial values. And this is 0.001 times the distance, and the distance is normalized by the input range. Not the range as defined here, but the range as defined in the model itself. And the distance penalty is super helpful, is a great addition to the optimizer that we implemented recently. It really gives you the flexibility to run the optimizer continuously, but without unnecessarily moving inputs around. It allows you to create process stability and optimization simultaneously. And when I go into a demonstration of the optimizer in action, you'll see how that works. That'll be the next video. I'm going to look at our optimizer targets tab now. So basically in this table, we're going to have one row for each output of our model. Now in this case, my model only has one output, but if you're using a model with multiple outputs, like for example, if you're modeling a grid of O2 sensors or something like that, or if you have a hybrid model, which we explained in another video, you're going to have 2 or more outputs in your model. And you can set different objective types for each model. For one output, you might want to be shooting for a specific set point, or you may want to maximize or minimize, or you may want to move into a range. And you can have different outputs with different objective types that you can all control programmatically, and you're going to want to assign them relative weights. Now you may want to give them equal weights, but if you have one that's very important and another that, okay, if we can do this in addition to getting the first one, that's nice, but it's not essential, then you might have a weight of 10 for that critical parameter and a weight of maybe 1, 2, or 3 for the secondary parameter. It's going to take a little bit of testing and tuning to figure out what the optimal combination of weights are going to be under different circumstances, and for that you can use the Test Optimizer button. This is a really handy feature. You can basically set up an optimization run and run it in real time. So for this scenario, I'm going to give ourselves a set point target of 10. We'll optimize, and there we go. We optimize. Our initial value was 2.097. I could play around with this, paste in our initial value, and it's basically going to stop immediately because our initial inputs, which are all 0, basically give us the correct solution immediately. If I change this a little bit, like let's just move it down to 2, then you see we get something completely different. Now, as an example of how the distance penalty takes effect, I'm going to check the use distance penalty option. Now you see these are all moving around substantially. If I optimize it again now, we basically have the minimum possible movement in order to get to our target of 2 from 0. From 0 at every input. Let's try making it 5 and see what happens. So you can see all of our inputs are pretty small. If I uncheck the distance penalty, let's try it again and see what happens. So we have a lot more larger values here, 0.5s, 0.7s, etc. So this is a quick example of how the distance penalty takes effect. And this Test Optimizer tool is really helpful for getting quick and dirty sample of what your optimization is going to do. Let's see what happens if we just try to maximize our output. So we got 14.434. That's indicating to me that that's probably about the maximum output we're going to get. I'm going to uncheck stop on convergence here and see if we get a little more consistent. Yeah, so 14.434 every time. So that's pretty much our model maximum. Let's try our minimum. And this is, of course, as limited by the minimums and maximums that we've defined. So let's look at our advanced settings. Now, you're not necessarily going to want to spend a whole lot of time mucking around on this tab. The default settings are going to work pretty well for you for most problems. You can pull up the particle swarm test tool from this window and play around with this. And you can change the behavior of the swarm. I covered these settings in a little bit more detail in a different video, but suffice it to say that the defaults here are going to be good for most problems. And in fact, we had stop on convergence checked in that example, but typically we're going to have stop on convergence not checked. That's the default. Yeah. So there are two more important areas that you may not have noticed when we were going through here, and that is the custom constraint and the custom cost. Now these we basically added in to give us just that last touch of flexibility that we needed the optimizer to have to really get it to work how we wanted in different types of problems. So in the next video, I'm going to actually run this optimizer and I'm going to show you how the inputs move around as a result of changing some of these different parameters, including the custom constraint and the custom cost. I'll see you in the next video.